Muchas gracias. Muy buenos días y bienvenidos a la Facultad de Ciencias de la Universidad Nacional Autónoma de México. Es para nosotros un gran honor contar hoy con la presencia del doctor Donald Bruce Dingwell, quien ayer fue galardonado con el grado de doctor honoris causa por nuestra universidad. Por favor, déjenme presentarles a las personas en nuestro presidium el día de hoy. La doctora Catalina Esther, directora de la Facultad de Ciencias de la UNAM. El doctor Hugo Delgado Granados, director del Instituto de Geofísica de la UNAM. Y nuestro invitado de honor, el doctor Donald Bruce Dingwell, director del Departamento de Ciencias de la Tierra y del Medio Ambiente de la Universidad de Múnich. A continuación, cedo la palabra a la doctora Catalina Stern para que nos dé unas palabras de bienvenida.
Hola a todos, gracias por estar aquí. La facultad sigue festejando sus 80 años y tenemos la suerte de que este año además se entregaron ayer varios doctorados honoris causa y nos da mucho gusto que colegas de otros institutos hayan escogido a la Facultad de Ciencias para que se impartan estas conferencias. El padrino del doctor Dingwell fue el doctor Hugo Delgado, pero nos pidió que se diera una plática aquí porque aquí es donde hay más estudiantes, así que espero que esta sala se llene muy pronto y que todos podamos aprender mucho. Welcome to the School of Science, and we're very happy and honored to have you here today. Y gracias a todos por estar aquí. Felicidades.
Muchas gracias, doctora Catalina Stern. A continuación vamos a ceder la palabra al doctor Hugo Delgado Granados, director del Instituto de Geofísica, para que nos ayude a presentar a nuestro invitado de honor.
Sí, tengan todos y todos ustedes muy buenos días. Realmente es un placer estar aquí en la Facultad de Ciencias. Gracias, Katy, por la hospitalidad. Es un placer realmente presentar al doctor Dingwell por su extensa trayectoria. Realmente cuesta mucho trabajo construir una semblanza de 2 páginas, pero vamos a intentar dar una semblanza de lo que él ha hecho. Él estudió Geología y Geofísica en la Universidad Memorial de Tierra, en donde se graduó con honores en 1980. En el 84 obtuvo el doctorado en Geología por la Universidad de Alberta con el tema Silicic Melts y sus implicaciones en la petrología ígnea. Trabajó en el laboratorio de geofísica del Instituto Carnegie en Washington por 2 años como investigador postdoctoral y en la Universidad de Toronto por 1 año como profesor asistente. En 1987 fue contratado como asistente del director del entonces nuevo Instituto de Investigación Experimental en Geoquímica y Geofísica de la Universidad de Bayreuth en Alemania, donde obtuvo su venia legendi en Geoquímica en 1992. A partir del año 2000 fue nombrado director del Instituto de Mineralogía y Petrología de la Universidad Ludwig-Maximilians de Múnich, donde fundó el Departamento de Ciencias de la Tierra y el Ambiente, del que es director hasta la fecha. El interés científico del Dr. Dingwell ha sido describir y entender los magmas y su impacto en los sistemas volcánicos. Sus investigaciones originales y novedosas cuentan más de 450 artículos científicos que están profusamente citados. Si ustedes buscan en Google Scholar, puede que lleguen a alrededor de 21.000 citas, convirtiéndolo en uno de los geocientíficos más citados del mundo. Su contribución ha tenido un impacto definitivo en el desarrollo de la vulcanología, particularmente en la vulcanología experimental, disciplina que desarrolló gracias a su creatividad e innovación. Don Dingwell tiene una reconocida trayectoria también como funcionario y representante gremial ante sociedades académicas profesionales internacionales y ha sido un incansable promotor del intercambio académico y de la colaboración internacional. Cuando fungió como secretario del Consejo Europeo de Investigación, el IRC, del 2011 a 2013, gestionó el Tratado Bilateral de Ciencias y Tecnología entre la Unión Europea y México. de hecho está vigente y pueden enviarse propuestas de investigación conjunta Unión Europea y México todavía. Ha dirigido grandes proyectos de investigación nacionales y europeos, así como ha promovido iniciativas de investigación en ciencias de la Tierra sólida. Su historial como formador de jóvenes geocientíficos es sobresaliente. Tiene más de 30 años de experiencia docente y ha supervisado estudiantes de todo el mundo, incluyendo estudiantes mexicanos, incluyendo más de 39 doctores, en una entusiasta promoción de los cursos. Es un entusiasta promotor de los cursos masivos abiertos en línea, los MOOC. Su curso Volcanic Eruptions on Material Science suman más de 20.000 participantes desde su inauguración en 2013. Todos están invitados a entrar a Coursera y lo pueden bajar y ingresar a este curso. Sus investigaciones sobre volcanes mexicanos, así como la interacción que ha tenido con investigadores y estudiantes mexicanos, incluyendo alumni de la Fundación Alexander von Humboldt, muestran su genuino interés en México. Sus aportaciones científicas lo han hecho acreedor a numerosas distinciones. Hay una muy larga lista, solamente les diré que un día antes de venir a México recibió la medalla de Viernes de la Asociación Mineralogía de Alemania, y las universidades de Alberta, en Canadá, y de Londres, en Inglaterra, le otorgaron también el grado de doctor honoris causa. En resumen, su obra ha influido profundamente en nuestra comprensión de las propiedades de los silicatos, vidrios y magmas, y en el impacto que estos ejercen en los procesos magmáticos, volcánicos y recientemente sísmicos. Su enfoque experimental para la manipulación de magma y lava a alta temperatura y presión permiten cuantificar los mecanismos físico-químicos que dan lugar al volcanismo explosivo. En particular, los desarrollados con descompresión súbita tienen implicaciones en procesos de yacimientos petroleros, es decir, va más allá de la vulcanología, su trabajo. Su exitosa trayectoria, para terminar, refleja tres cosas. En primer lugar, su talento para la experimentación creativa y para identificar y medir parámetros críticos. En segundo lugar, su generosidad para la investigación colaborativa. Hay una afluencia constante de científicos y estudiantes que visitan su laboratorio de vulcanología experimental en Múnich. Y en tercer lugar, sus trabajos sobre volcanes mexicanos en colaboración con científicos y estudiantes nacionales e internacionales muestran su genuino interés en México. Esto último ha permitido establecer una cooperación fructífera entre los científicos mexicanos y alemanes. Muchas gracias.
Muchísimas gracias, doctor Delgado. Y vamos a dar paso a la conferencia del doctor Dingwell, por lo que les pediré al doctor Delgado y a la doctora Stern que bajemos. Y a continuación, Volcanic Last, The Forgotten Phase, por el doctor Donald Dingwell.
Good morning. It's an enormous pleasure to be here today. And yesterday we had a wonderful ceremony, but today we're going to have much more fun because we're going to talk about a phase, a state of a part of the system of all of volcanism and all of the processes in the deep earth which contribute to volcanism, magmatic processes, and that is the glass or the melt phase. Since the advent of modern mineralogy about 100 years ago, with the discovery of the diffraction of X-rays, mineralogy, due to the regular structure of minerals, has made tremendous advances in solid-state physics, and one can detail much of the history of rocks based upon the mineralogical analysis, the zoning, the structure, the chemistry of the mineral phases of rocks. And so solid earth materials has always been dominated by the study of minerals. In fact, we have the whole branch of earth sciences which we call mineralogy. At the same time, the revolution of X-ray diffraction did very little for helping with understanding the structure of glasses because they are amorphous, they do not have a regular structure. They are simply quenched samples of the liquid, and they have not undergone any phase change into a crystalline state. And so they've been, if you will, the forgotten phase. They've been the phase which everybody recognized on a superficial level. Everybody said, yes, we need them, otherwise we have no volcano, we have no liquid, we have no magma. They are the most important phase with regard to the transport of these systems, and it's all about transport from down there to up here. And yet, they are the hardest part of the equation to solve. So there is, however, some hope to quantify some of the message which glasses bring to us from volcanoes. And what I want to do now is take the next half hour or so and explain to you one branch of this work, which is to analyze what we call the thermal history of glasses. It's a particular attribute, a particular property of the glassy state, well known in the glass industry, well used in the glass industry. And what we did a couple of decades ago was to take that technique and that information and to turn it back to natural glasses and ask the question, can we use things from glass to infer things about a volcano? The volcanic system itself, just one or two sentences, no more, because I realize the room is very broad in background. The volcanic system is absolutely fascinating and absolutely essential to the Earth system. One does not hear much about volcanoes in the Earth system. Most of the attention is given to the sedimentary record, the currents of the oceans, the state of our atmosphere, but in the background, permanently, continually, we have contributions from the depths of the Earth, which are here described with the word lithosphere, the rocky layer of the Earth, punctually being sent up into every other sphere of the Earth system. So this is the way that the lithosphere talks, has a conversation with everything above the surface of the Earth. The hydrosphere, the oceans, the atmosphere, the anthroposphere, if we want to say, ourselves, the biosphere, of course, in general, and so on. And so we can be fascinated by volcanic processes, and almost all of us are fascinated by volcanic processes who work on volcanoes. But we must not forget the impact that volcanoes have on a much broader field, on a much greater global sense. So they're at the very center, of what we today call Earth system sciences. This slide is in German, but most of the words are close to English. What I want to say with this slide is that you're about to see an experimental analysis of products of volcanoes. And to do experiments and to make progress experimentally, you all know that you have to quite often simplify the system in order to know that you can isolate the number of independent variables, play with the number of independent variables, and get some causal relationships which explain the dependent variables. What I have here is a simple, linear picture of a volcanic system. I'm sure it does not look simple to you, but believe me, it's a simplification. We used to look at volcanoes as a simple linear sequence of events which we believe must occur from saturation, nucleation of bubbles, growth of the bubbles, foaming of the liquid, very important, and fragmentation of the system below the surface of the Earth. The products of this sequence of events are the products of the volcano, and the products of the volcano come in many forms. They come morphologically in the form of lava flows, in the form of debris avalanches, in the form of hot, what we call pyroclastic flows, and they also come in the form of clouds, which, as you probably know, can rise to the stratosphere and can be globally distributed, so that you can shut down airports in New Zealand from an eruption in Chile within days. So these things are spectacular in their variety, but in all of them, And in all of these processes, it is the melt phase which is deliberating the system, which is defining the system, and the melt phase, which does not succeed to crystallize, is giving us the glass. And the fundamental physical principle, which allows us to talk about melt on one side, or liquid on one side, and glass on the other, is now a very old idea, over 100 years old, which we call the glass transition. And the glass transition was not defined by geoscientists, it was defined by glass scientists. At a time when they wanted to perfect the optical properties of glass for many reasons, they found that they had to perfect the pouring of glass, the production of glass from a glass melt. And in order to do that, they had to get this phenomenon, the glass transition, precisely under control. And so they deliver for us a quantification which we can then apply to natural glasses. Essentially what you look at is a time scale here. These are fast processes, these are slow processes, and a temperature scale. Hot on the left, cold on the right. So in essence, an Arrhenian temperature dependence of these. Right away, you see that the line itself is not Arrhenian, it's non-Arrhenian, but it is significantly linearized by plotting it as a function of reciprocal temperature. Now this, finally, is a picture of what we're talking about here the whole time. These are pyroclasts. These are fine-grained samples of exploded magmatic systems, volcanic ash. And what you can see is two different pictures of them. You can see on the upper right an electron microscopy picture, which allows you to see very nicely the morphology of these particles. So you can see a fair degree of complexity in the morphology of these particles. Essentially what you see, everything hard and solid that you see on the upper left is glass with embedded crystals, whereas what looks like holes, I hope looks like holes to you, is where the magmatic gas was residing at the point of explosion. Okay? On the lower right, you see an optical picture of the system. It looks a little more complicated because the optical properties between crystals and glass are very different, and they're very easy to distinguish. That's why we use optical analysis of rocks. And you can see that there are a clear white phase, which looks like broken pieces of glass. It literally looks as though you took a water glass, crushed it up, put it under a microscope, and you would observe a very similar thing. So the glassy phase, the white colored phase here, is dominating. There are other phases. There are crystal fragments which are here, including the black parts that you see. But the matrix, the host of the whole system, is a glassy phase. Now, the properties of these magnets which come up through the Earth are spectacularly variable. If you wanted a physical-chemical problem to play with in classical physics, you couldn't get a better system than a volcano. And I've heard many physicists over the years tell me it's the easiest thing in the world to explain to first-year physics students how you can play with classical physics is to take a volcanic system. It really has everything. This is just one example of what the physical system has. It is the viscosity versus the water content. These are wet systems. They have a lot of water in them at depth. When they rise to the surface, it's no longer possible to hold the water because the solubility of the water depends on pressure. So the decompression of these rocks coming to the surface results in loss of water. It simply means that as you rise to the surface, you go from the right to the left. And you can see the immediate consequence of going from the right to the left in terms of the viscosity. The viscosity, which is controlling the stresses, which drive the strain rate. And it's a very catastrophic situation, at least on the Earth, where we see that the water contents, which would be stable at the surface of the Earth, correspond to liquids with extremely increased viscosity. So as you're coming from below, driving to the surface of the Earth, you hit a crisis of viscosity. And the crisis of viscosity gives us the possibility to capture the glass. Because highly viscous liquids cannot crystallize very easily. And this is the fundamental reason that we get glass from volcanic eruptions instead of the alternative, which would be 100% crystallization, or vanishing of the liquid phase. Another point about these flowing systems is that the distribution of stress, volumetric stress or pressure, as you come up the system from the 5,000 meters depth up to the surface of the Earth. Normally in geoscience, we calculate what we call the lithostatic pressure, literally the weight of the pile of rocks down to the depth that you're interested in. You could do the same thing with a magma static pressure. You simply take the density of the magma, calculate the depth, rho, GH, and you have your stress at the bottom. But this curve in a flowing system deviates drastically from the lithostatic or magmastatic situation, because in a flowing system, the stress is no longer distributed as in a lithostatic system. The stress is distributed in a flowing system by the viscosity of the liquid. And if you have a high viscosity, you have a high rate of change of the stress. If you have a low viscosity, you have a low rate of change of the stress. So as we go from depth to the surface, lose the water, make the system more viscous, we drive it to an extreme state of decompression. And this extreme state of decompression leads to fragmentation. Now I just have two quick videos. You'll see if I achieve playing them, but it's just to remind you that this liquid-solid transition is everything to do with volcanoes. So literally, it's how do we go from liquid to rock, magma to rock. Here you see the front of a lava flow in Etna. If you look carefully, you see people walking in and walking out. So this is a very safe place to be, actually. You know exactly what's coming. But what you see is, if you look in a defocused way, you see obviously a tongue of rock, the flow coming down as one body. So it's obviously viscously deforming as a whole. But if you look more focused, it's also immediately clear to you that on the front of the lava flow you have blocks falling off of the lava flow, which are broken, fragmented rubble, which has been produced by breaking material. Now, breaking a liquid is not very easy. Breaking a solid is relatively easy. So this has gone from a liquid to a solid state in the presence of a liquid component. More spectacularly, we sometimes have very viscous lava which sits on the top of a volcano and behaves like a glacier. It flows slowly down the sides of a volcano. And these flows can become unstable, and in the same sense that a glacier can calve off, and everybody today has seen pictures of glaciers falling, pieces falling off the front of a glacier. Here you have pieces falling off the front of a volcanic glacier. And you see it behaves very differently than a glacier. This cloud will grow and grow and grow because it contains a tremendous amount of thermal energy, and it sucks in air from the sides. And as a result, you get a larger and larger and larger fraction of air to rock. And this is the most dangerous thing that a volcanic eruption can do. There's no way to avoid this. Running away is really not an option. And this was actually, I should say, this was a tragic event which is portrayed here, which led to the deaths of a number of people observing the volcano, two of whom were the Kraft family, after which a medal was named, which has been in the meantime conveyed to your professor, Hugo Delgado. So let's get back in the safe lab and let's take these pieces apart, like we learned to do in high school in science class. So here you go, you have time and temperature, you have it again. Now here is our map for investigating these materials. There's two ways to do it, A and B. A means you go above the liquid temperature and you simply play with liquid physics and liquid chemistry above the melting point. You can do it as long as you want, nothing is going to happen, the liquid is stable, it's thermodynamically in the lowest energy state, you're fine. Okay, that's the classic way of investigating any low viscosity liquid. But you can also do B. This was controversial. My PhD supervisor never believed this. That's not that long ago. Okay? He rejected papers based on this kind of work. But you can do it because it's a metastable way of determining the properties of silicate melts. So you can do A in the stable regime of liquids, but you can also do B because these liquids do not crystallize easily. They stay as a liquid state even though they are metastable. They could crystallize any moment. You have to be on guard. You have to be observing very carefully. But if you can avoid crystallization, you can play with them as if they are stable. Okay? That's basically metastability. So what we do is we look at one property, and the next 10 or 15 minutes will be all about this one property. It is the heat capacity. This is a diagram from an old German textbook called Glass. And what they describe is this strange jump or bump in the value of the heat capacity. Okay, so the amount of energy I need to move this material up 1 degree for a certain mass unit, right? You would think that it's smoothly changing with temperature. In all crystalline substances, as long as they don't undergo a phase transition, they will give you a smooth temperature dependence of glass transition from the bottom to the top. Right? In this case, you don't get a smooth transition from the bottom to the top or from the left to the right. What you get is a transition somehow, a jump. Here is an example of boron oxide. You heat it up, it has a low value of glass heat capacity, and suddenly it has a higher value of heat capacity. The same thing for zinc chloride, the same thing for silica glass, the same thing for window glass, the same thing for metallic glass. Okay, glasses can be made from any liquid if we can establish the right experimental conditions. So all of these things show this jump in heat capacity, and this jump in heat capacity is the gas transition. And the reason that the heat capacity jumps is because you're going from a solid-like behavior of the liquid or a solid-like behavior of the melt to a liquid-like behavior of the melt. The structure doesn't change. The structure is amorphous all across the diagram, but the structure is frozen on the left-hand side, and the structure awakens at that jump and then participates in the further energy cost of heating up the liquid through diffusion and through a redistribution of the structure of the liquid. And that costs energy. So if we can capture the details of this transition, maybe we can say something about the conditions under which the glass was formed. And the basic idea is this. You have the state of the glass, density, enthalpy, you could put any thermodynamic property in here, and you plot it versus the temperature. When you're at high temperature, you see that there is a one-to-one relationship between the TF, the fictive temperature as we call it, and the actual temperature of the sample. Everything here is very, very simple. It means that when I have a liquid, by definition, its density will be at equilibrium. Its density will be the density it should have at this pressure and at this temperature. It never deviates. That's the definition of a liquid. Huh? But if I make the solid at low temperature, then you see that the density doesn't change as a function of temperature. Very bizarre. It actually changes a small amount elastically, but it doesn't change the viscosity. It means that you've frozen the structure. You've locked out the possibility of this glass relaxing right here at the glass transition. And what you see is that the cooling path, which has the arrow going down, and the heating path at the same rate, which has the arrow going up, are very different in where the density will be. It means there's hysteresis here. It means there is a path dependence of the state of the glass. And that is the key. If we know that there is a path dependence of the state that we're investigating, then we know we can get kinetic information from that state. That is the message. Okay? So we do that. We can plot where these TGs are as a function of absolute time, relaxation time, and absolute temperature in this manner for various chemical compositions. And you see that changing the chemistry of these glasses from high silica to low silica has a huge effect on the viscosity and the relaxation. An enormous effect. So changing the chemistry of a volcanic liquid a little bit will pick it up immediately in looking at the glass transition. Okay. We also know that the tensor of the stress which is involved at the glass transition is not important for us, because no matter how we measure the viscosity of the liquids, if we measure it in simple shear, or if we measure it in so-called longitudinal viscosity, so that we have a volume component of deformation, these things are decompressing. There is a volume component of deformation. As they come up, they become less dense. It doesn't matter. We get a very simple relationship between the two. This is the most dramatic example of the effect of chemistry on the glass transition that I can give you. There it is. You add water, you add water to a silicate melt, and you see that the glass transition drops 400 degrees as a function of a few weight percent of water. So water, and water coming out of that liquid, is the crisis that I referred to before. Now you see quantitatively why it's a crisis, because this solid or solidification temperature of the glass is coming up 400 degrees. Just as you're cooling down, it's coming up to meet you. It's really a crisis. Okay. This is an example of the fact that you can, no matter how you measure the glass transition, you always get the same result. So the peak here refers to the glass transition. And you see here, it's a CP, it's measured with a calorimeter. But actually here you see dV/dt, volume versus temperature. It's obviously not measured with a calorimeter, it's measured with a dilatometer. It's something which is measuring the dimensions of the sample, and yet it gives exactly the same results for the glass transition. All of these things, all of the properties that can be used to measure the glass transition, they all fall back to one value of glass transition, because it is the viscosity and its temperature dependence which is controlling the glass transition. So, how do we try to apply this to really make a livelihood and make a business out of all of this theoretical information? We try to get the thermal history from volcanic glass. It's as simple as that. There's two basic ways to do it. Either you determine the quenched-in properties of the glass at room temperature, you go out to the volcano, you shovel up the ash, measure the density of the glass in the ash. In principle, absolutely simple. You'd be embarrassed to tell your mother that you did this for a living. But in detail, to do it, as is so often the case in physical science, in detail, to do it with the precision you would need is virtually impossible. Okay? So this technique, although absolutely trivial to explain to you, turns out to be practically, and this is the life of an experimentalist, you always have to know what is practical, what is a significant investment there. So the other way we can do it is this one. This one is much more complicated to explain to your mother, but the basic idea is you take the glass, you heat it back up across the glass transition, so you literally drive it into the liquid state again in a calorimeter, and you watch how it relaxes as it goes back to the liquid state. And how it relaxes, exactly measured, gives you the hysteresis, which you can use to interpret the initial cooling rate of the glass. Okay. So details of the method, I won't go into them because we have a lot of material to cover. But basically, the frozen glass structure depends on the rate at which the glass transition is crossed in its production. And we want to observe some structure-dependent property, enthalpy or volume. We need a model of the process to quantify our results. And we need to be able to calibrate. And for the experimentalist, this is the holy grail, of course. We need to be able to calibrate how well we can do these determinations. Otherwise, it's just a nice idea. This is a terrible flow diagram which shows you the calibration. This is to drive home the point that if I have one single liquid here and I cool it at different rates, here are the rates, 100 degrees per minute, 10 degrees per minute, and 1 degree per minute, it will lock in a different temperature value of freezing, a different so-called fictive temperature as a function of rate. This is just another way of describing this dependence. So this is what an experimental curve looks like for a natural glass. For those who are volcanological, this is a per alkaline rhyolite. It means it's a high silica glass, but it has a lot of alkalis. And you can see right away, the first thing I can tell you right off the bat, without much ado, is that within this range, going from a solid here to a liquid here, so in a range of about 470 up to about 570 perhaps, it has gone from being a flowing lava to a solid rock. So right away, first number, take it. You don't need to know anything more about rates. This thing stopped moving at 650 degrees Celsius. So you can imagine that if you have the job to go out and map a mountain, to map the hazards which are associated with that mountain, and you're trying to do a physical-chemical model perhaps of how these lava flows will progress down the mountain, one of the valuable things that would be there for you to know is what temperature does it stop at? And as simple as that, we can deliver the first number of such a raw curve, okay? But of course we take it further. We do everything we possibly can in the lab. We have to pay for the machine after all. So here we go. This is the raw data. This is from another sample now, but it's a raw data. Here you see naturally cooled. I heated it up, and this is the signal that I got from the calorimeter. Then I leave the sample in the calorimeter and I cool it down at a known rate. That means I decide the cooling rate of the glass. And then I heat it up again and record what the calibrated signal is for that cooling rate. And then I cool it down at another rate, half as fast. I heat it up again, and I get another calibration curve. And I walk myself here, back and forth, back and forth, to a range of cooling rates that I can access in the lab. Now, unfortunately, the range of cooling rates that the calorimeter will endure, it has limits on the slow side of signal intensity, it has limits on the fast side of temperature gradients. Anybody who's done any calorimetry knows there's only a certain set range of rates that you can use any particular type of calorimeter for. They limit what I can do for a calibration, but they allow me to calculate out the material-specific parameters that I can use to estimate what this cooling rate was. So simple as that, okay? But actually the practical trick, which made it all possible, was simply thinking about how we could get this calibration good enough that we could use it for determining natural rates. Maybe one word for those who are interested. There's two major issues in this kind of measurement. There is the non-exponentiality of relaxation. I'll just say it for those who might know and keep away what that means. It means that the relaxation curve as a function of time is not fitted to a simple single relaxation time or an exponential decay. And we've known that since about 1890. And the other thing is it's a nonlinear process, because as I heat the sample up in the calorimeter, the target that the relaxation is trying to go towards is a moving target, because the temperature is changing, and the equilibrium state changes as a function of temperature. So this is why these curves look a little bit weird. You're dealing with nonlinearity, non-exponentiality at the same time, okay? All right, so we fit these curves. This is just to give you a taste of how accurately we can do it. This is the raw curve dashed and the model curve solid, so we consider that a very good fit. And if we change it by a factor of 2 sounds like a lot for a physical scientist, but remember this is a logarithmic variation of viscosity, then we miss it horribly, okay? We go the other way, we miss it horribly the other way. So we can do this much better than a factor of 2. We can do it to within perhaps a 10th of a log unit of cooling rate. So the question is, and this is what every experimentalist face, okay, now I know how well I can measure it. Now you pray that nature will give you a playing field of variation of what you're measuring, which is larger than what you can measure, than the precision with which you can measure it, right? And then you know it's a useful tool or it's just a theoretical interesting exercise. Huh? And the good news is nature gives us a tremendous playing field of cooling rate. And here you go. You have the log of the cooling rate. You're looking here at 7 log units of cooling rate of volcanic glass in nature. It's fantastic. Nature is producing these glasses in an instant, to use a work term, and it's producing these glasses by baking them over years as they cool slowly down through the glass transition. And the whole range gives us 5 or 6 log units that you can see here. These are real results. Every big box corresponds to an actual natural cool glass. Over on this side you can see they come down from degrees per second to degrees per day. And so if this is a characteristic of volcanic glass, you can go out into the field blindly, take glass samples, you can have an idea of how this unit of glass formed in the field. That's a big part of modern volcanology. But you can go back to the lab and you can measure the cooling rate and you can say, is it reasonable that this cooling rate could be formed with this physical model of how this outcrop of glassy rock formed? So I had a geological training despite my lab work, and so I really wanted this to be going out into the field and people to try to use field examples of whether it was useful. So we went several places in the early years. We went to Roche, which is a beautiful black glassy lava flow in Ypres. We got beautiful data for beautiful glass. This is the raw data right here. As usual, it cooled more slowly than our calorimeter. It's higher than our calorimeter. Then we calibrate it back and forth, back and forth, back and forth at these rates. And we estimate a cooling rate based upon extrapolation to that value. And these are the cooling rates we estimate by going from the top to the bottom of a glassy lava flow. So relatively fast cooling rates. This is the minus the log of the quench rate. So relatively fast cooling rates at the bottom and at the top of the lava flow, and then slower cooling rates in the interior. So by the time this was going on, there were all kinds of really bright people thermally modeling all these things and giving you the answer, but they had nothing to calibrate their models on. So this is just an honest experimentalist saying, here are the cooling rates you have to get as a result of your model for cooling of this model. And there are 100 of them in all of us, so it's a great time. Okay, these are glasses which are very difficult to get. They're basaltic glasses. Basaltic rocks have low viscosity, with or without water, so they usually crystallize very beautifully. And as a result, you get almost no glass. The only glass you get in a basaltic eruption is a small length scale of glass. You can get it on the edge of pillow lava erupted into water. You can get it in explosive scenarios where the glass is fragmented into very small parts. But if you go outside of this building and walk across a basaltic lava flow somewhere here, you're probably looking at something, and I looked at Google for correction, but you're probably looking at something which is virtually completely crystallized. Okay? Nevertheless, if you scratch and stare long enough, you can find glass. And here we determine a few glass transitions for basaltic glasses. You see that they are cooled here at relatively slow cooling rates, so it's remarkable that these glasses are preserved. Let me jump ahead. One more example, Tenerife caldera. If you ever want to be introduced to what a volcanic field looks like and you want to do it somewhere else besides your back garden, go to Tenerife, the second largest volcanic island in the world, and you will see spectacular exposure of lava flows. Anybody can be a volcanologist in Tenerife, and that's why we went there. You have your beautiful caldera in the middle, and you have Pico de Teide, which is the peak of it. And so we went and did glassy lava flows there. This is the range of cooling rate which we got within a single volcanic field. So we got samples which cooled at rates of 10 to the 1 to 10 to the minus 4, 5 log units variation of cooling rate for one chemistry, one volcanic system, one volcanic phenomenon. Okay? It means that there are widely different fates which are experienced by these volcanic glasses. This is the most extremely slowly cooled glass we've ever seen. It's from Mare Island in New Zealand. It's a glass which won't crystallize no matter what you do to it. It's a very special chemistry. Okay. Let me jump through. Now I jump to the newest frontier of all of this. It's the future now, which I'm going to talk about, which is even more difficult. This is the latest in high-speed calorimetry. It's called flash calorimetry. It's produced by a company in Switzerland. We just got one delivered last week in Munich. So while I'm here having a good time, some people are working in the laboratory in Munich. And this one works on the basis of solid-state chips. They are hit with a flash of heating, and they are relaxed at heating and cooling rates which are thousands and tens of thousands of degrees per second. Now you can guess that if you're going to do something at that speed and get something reasonable for a finite sample, it has to be very, 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 very small. And so this is the frontier. This will allow us to do 10 micron samples. 10 micron samples means we can go into complex ash, where we have crystals, bubbles, glass, and we can actually pick out a fraction of that by crushing it, and we can extract and we can isolate a glassy phase of a very fine-grained material, and that opens up all kinds of frontiers for us in determining the thermal history of glasses. The problem with doing a bulk sample of many phases is that often, if it's fine-grained, the glass will react with everything else in it, which is sulfides, oxides. It's a real mess. Volcanoes have the whole periodic table. So the hope and the belief is that this fast calorimetry will allow us to isolate fine-grained glassy samples, which will allow us to go into a whole different level of surgery, if you will, and to discover how these things vary in nature. So these are upside down, but you see these are glass transition curves. Okay, right here. And look at the cooling rate, 30,000 Kelvin per second. So this is clearly something which is very, very small and doesn't have much thermal mass. You can see that it shifts with cooling rate, as it should. And you can plot it as a function of cooling rate, as a function of temperature. You can see it lines up with the temperature dependence of viscosity, as it should. It works like a charm. Absolutely works like a charm. We know where it stops working. We've changed the heating rate here. And we can see that beyond a certain value of heating rate, the value of what we're trying to measure runs away. That means we're losing it. The machine no longer has it completely under control, but you can see where that happens. So we can really drive right up to the edge of the precipice and play there as long as we want. And we know if we fall off. Okay? And you can see here the onset in temperature. So this is 157. This is 160 degrees. Only 3 degrees. This is a calibration using indium metal, which we use for the device. So what will we use this for in the future? Now I'm the prophet. I'm going to predict to you now something which hasn't happened yet. But there are many ideas which immediately come to mind. And so much of good natural science is the combination of the most recent technology and then the people who are not developing the technology, and I am not somebody who's developing the technology, but they know the problem very well. And this marriage of the technologist and the person who's coming with the best knowledge of the problem, this is so often where science goes forward really fast. And for us, it's probably going to be in the following areas. Ash monitoring. We get ash samples from volcanoes routinely. Professor Delgado has an archive of ash samples running over decades here. They've never been measured in this way. We can have a very sophisticated expectation where we say we want a complete description of the plumbing of this volcano, and we start to build it based upon the cooling rates of what comes out. But we're not going to do that. We're going to be very pragmatic, as geologists often are. I suggested to Professor Delgado, we simply measure all of the ashes over time. Do they all give the same number? Does the number drift with time? Are there inflections in what we get for a cooling rate of what's coming out of the volcano? And if we see inflections, what the hell does it mean? Does it mean that the system is shifting into another state due to progressive erosion of subsurface structures? It opens up a whole new playing field of the kind of questions that you might ask about the state of what's just below the surface of Popocatépetl, for example. And that's where these ashes are coming from, and that's where if you see something move, then your alert level will go up because you know that there might be something different to expect tomorrow than you saw yesterday. Okay? The second one is that we can get to these finely distributed glass phases, so the rhines, the interstitial glasses, the messy systems, where they're dominated by crystals. But if you look carefully enough up, there's the glass. We can take that glass out now, and we can get its cooling rate, despite the fact that it's a small fraction of the total. We can also go in and do micro drilling. We can drill down to tens of microns today, and we might be able to do profiles where we can pull out gradients and heating rate from these systems, which will also tell us something about their origin. But I actually dream of doing number 4 because it's never been done, and that is the idea of there are packages of these glasses which are contained within the erupted crystals of rocks. And those packages are messengers from the deep because the crystals were formed in the deep. They captured these liquids in the deep. These liquids in these packages are before the magmatic ascent to eruption, and you have the glassy shards which are after the ascent to magmatic eruption. If you have both, how much more that is than if you only have one. And so the hope is that we'll be able to isolate melt inclusions because we can certainly do the length scale. We can do it on tens of microns and the inclusions get that large. And the last one, lava emplacement dynamics, I think it explains itself, but if I will go out now and do a 3-dimensional sampling by shallow drilling and by selection of a lava flow, then I have a good chance to be able to describe how that lava rock was created in what may seem to you to be a very simple thing. Well, it started up there and it ended down there. What's the big deal? But if you look in detail at pictures of the surface of Hawaiian lava flows, then you see how complex this solidification is, because you see flows of solid rock floating down the liquid flow. You see redistribution to the sides, to the ramps of the flows, called levees. There's a lot left to understood about the dynamics, to be understood about the dynamics of these systems. And just to give you a finish, I'll just give you a picture of the complexity of some of this material. This is the kind of material that we can build in the lab. This is 10 microns. These are the bubbles that we can grow in the laboratory. If you look close enough, you can see very strange features here in these experimental samples, like a pairwise structure of bubbles. You see that? We can also put in gradients in stress and elongate the bubbles, as we commonly see in basalt, and as you'll see if you walk out of the building and walk along some part of the local scenery. We can even drive them to the most extreme state we know, which is so-called tube pumices. These are bubbles in rock which are 1,000 times longer than they are wide. It's incredible what nature gives us. We get eruptions which give us this, and also give us the other simple kind of porous rock. Why? Why do we get these two things? We obviously have two different stress regimes in the eruptive system. And with this microanalytical technique, we can actually go in now, pick out these bubble walls, and see if they suffer a different thermal history than the simple rocks that they were calling like. So, simple, in one sentence to sum it all up, the frontier of this stuff is scale. We've been able to reduce the scale now by a factor of 100 or 1,000 that will allow us to go in a microscopic way and see, in the sense of thermal history, far more than we've been able to see before. So we're very, very excited to get back to Munich and see what the first samples from over the day will show us. Thank you very much.